All right, so let's get started. Well, good morning, evening, or afternoon, depending on when you're watching this. So I'm sorry I've not been able to put out, you know, a few put out streams as much as I can because I've been dealing with a personal loss in my family. So I've pretty much been away from work. But yeah, now I'm back. And today I just want to continue the Rust. Um, we discussed Pliron. I guess you can check out part one. This is going to be part two, where in part one, I talked about what Pliron is, how it's an equivalent to MLIR, but except that it's not written in C++ or C, it's written in Rust. And we've talked about the design of Pliron, things like its usage of arenas or generational arenas, a lot of macro usage so that you can effectively um, simplify the way you write some of this code in Pliron, and extensibility, which is the hallmark of something like MLIR or Pliron. It's going to be how can we extend, um, compiler IR. But just to recap a bunch of things. So MLIR, like MLIR, Pliron is a nested IR in the sense that you can have things like operations, which contain regions, which contain blocks. And within the block, you can again have operations which can contain regions, which can contain blocks. And there's a lot of usage for this in the compiler space. You could effectively come up with a custom IR for your own domain. And we've sort of discussed this with an example. For example, we looked at the Triton dialect. This is something from OpenAI. They use it for, you know, in that Triton language, which is what they use for building their LLMs and stuff. So you could take the Triton language, you can sort of create a custom IR for this, and then you could do your optimizations in this IR because you're in the right language with the right, you're in the right representation rather, and you'd be able to go ahead and apply the right kind of optimizations at this level for the particular hardware you're targeting. So we sort of went through all of this, and I went through one of these examples as well and talked about the core data structures in Pliron being the context, the operation, etc. And I gave you a brief view about what the generational arenas concept is. Um, it's basically, you don't want to because programmed, um, program information about your program is usually things like, for example, if you remember what I mentioned, if you look at this representation, each statement has some information. There's a person 0 that equals tt dot get program index. X is possibly an argument. So, and this is probably the return value. So you need to different components of your program or your representation will need to be stored for either for modification or for querying or for, basically analysis, whatever it is. Uh, that's the crux of what you do in compiler engineering. So the way to do that is you'd want to keep that storage as efficient as possible. Generational arenas are one of them. And yeah, we've discussed a whole bunch of things uh, in terms of the core data structures like context, which pretty much stores the entire state of your um, right word would be a compilation session, right? So yeah, without diving too much and recapping the whole thing, because it's been a while. So I'll leave you to it. I'll just link the previous video so that you'll be able to quickly watch that if that's something that you want to see. And now what I want to actually do is I want to get to, because in the last one, What I missed out was um, the implementation aspect. So we walked through, we evaluated, we looked at the design of Pliron, but we never went over the implementation. How do I add a dialect to Pliron? So there's a goal that I have. Uh, if you remember, we've done some screens on the Cranelift IR, which is another compiler backend or code generator, but that's again completely written in Rust. So that compiler backend has its own IR called Cranelift IR, and I've done a bunch of videos about that, so you can look them up. That so what I basically want to do is take that IR and convert that into Pliron's version of that IR. So once it's in Pliron's version of that IR, I can do a bunch of optimizations and then move it along, you know, the same code generator and get some and target some specific hardware for it. So so this particular stream, what I want to do is keep it as concise as possible and only focus on the implementation. And if you just focus on the implementation, I guess it's going to be pretty simple. So we discussed what a Pliron operation is, and the data structure looks like this. Well, it'll have something like an op ID. This is basically a string of some sort. It'll have a dialect name and op name in it. And then it'll have a pointer to itself. And I already told you that when we say pointer, we basically mean it's a reference. It's like you store the actual thing in some container and you get a reference back to that that you can use, with whatever you want to do with it. So the storage is separated from the usage. And there's actual usage, and there's an actual reason for this. You can again watch the first stream so that you get a better idea. Cranelift does this, so does Pliron. Um, and then you can see things like results and operands, they're all just vectors containing, the result of an operation of or an operand, etc. All that's very straightforward. And then you've also got things like what is the list of basic blocks that make up a particular function. In my case, because I'm working with Cranelift IR, every function is a compilation unit. So that's why just want to stick with that. When we say basic block, the list of basic blocks, I'm referring to list of basic blocks within a particular given function. And then you'll see in the implementation as well, one of the important things is you want to be able to link, the sequence of blocks. Which block is the parent of the subsequent block or whatever block that follows it, or which one's the child. And that's usually done using a linked list. That's what Pliron uses. And that stuff is stored here as well. And then there's attribute dictionaries that we also have. And then regions. All this stuff is extra. I mean, when you use it, you use it. But this stuff is what you end up using quite a bit. So now let's get to the part as to how do we define or how do we write, uh, how do we basically convert Cranelift IR into Pliron's version of the IR. So the best way to do that is to actually show you an example of what Cranelift IR looks like. So if you were to go ahead and look at what Cranelift IR looks like, not to show you a very convoluted one, so let me just find the simplest one. So Cranelift IR looks like this. It has function, the name, the arguments, the return value, and this is usually the calling convention for the architecture. This is for the Apple architecture. And then you can straight off start with a block. A block will have its block arguments, like LLVM, where you have five nodes, etc. You don't have that here. And then you have the operation, which is IAD. In this case, it's an integer add, takes two values and returns a zero. And this is basically what Cranelift IR looks like. This I would like to convert this to something that looks like, okay, something that looks a little more interesting. But let me just run this for you so that you can see it clearly rather than looking at the that's uh, sorry, I just have to change the names and shit. So yeah, so yeah, I want to convert whatever you just saw into this. That means this portion, sorry, this portion into this. So and you can see the structure remains the same. It's still a function. The name still add. It still takes arguments. But just the way we represent this is going to be different. Because once this is in the Pliron format, I have this entire Pliron infrastructure that is available to me to make interesting optimizations the way I see fit for a given problem, right? That's the goal. So how do you do this actually? So what we've done is, first things first, you've got to take a look at if you take a look at the repo, there's already an implementation for LLVM, which is called Pliron LLVM. And then the source folder, and then you'll find a bunch of files. So I pretty much looked at that and said, let me go ahead and use the same format. So Pliron-CLIF is my implementation for the Cranelift IR to Pliron, the Pliron version of that IR, which is Pliron-CLIF. So for now, it's got the necessary opcodes, which means it's got most of what we need to sort of implement pretty much the IR. By the way, the Cranelift IR actually has about 107 different opcodes, which I've sort of captured over here. So you can go ahead and see them. These are all the opcodes. I don't know if you can see this. Yeah, that should be better. So there's about 107 variants as on 15th Feb when I checked last. But yeah, you don't have to worry too much about all of them. If you can go ahead and convert the main ops, um, the ops that are the most recurring, and then most of the thing is just a repetition, and there's just some ops that may be a little more involved, like let's say atomic operations, etc. But that's all later stuff. But for the most part, you'll be able to get through. So I think I've already implemented about 10 something like that. And the implementation was mostly copy paste depending on what op I was implementing. But yeah, so that's one. Then so the first thing to do is you go ahead and you have to define your operations so all of the Cranelift operations must be, you must have an equivalent to that in the Pliron world. The way to do that, let's take a simple example, the return operation. So if you saw this, wait a minute. So if you saw this is the return. This is the return operation in what you'd call Cranelift, right? Now, I want an equivalent for that in my IR. And an equivalent for that is something that I create. So the way you do this is, as I mentioned over here, the first thing you need to do is, I'm sorry about that. Just a minute. Yeah, the first thing that you need to do is you go ahead and annotate that particular a unit struct with this macro. And this is why, if you remember, we talked about exhaustive usage of macros in, not exhaustive, heavy usage of macros in Pliron. It's because of this. A lot of the stuff that you don't need to write by hand, you can just, use a macro for that. So if I want to have some uh, type that is a Pliron op, all I got to do is take a unit type of that and annotate that unit type with this particular macro, which is def op. That's what I've done over here. That's what you can see there. And then you can clearly call out what your what that name of the op is. The dialect, which is CLIF, and then name of the op, which is return. And if you do that, you see this is what you'll end up with, right? So once you do that, the next thing that you need to do is pretty simple. We already discussed interfaces that are what gives Pliron its power, because you can extend the IR as much as you want, the way you want. And in order to do that, the way Pliron does that is MLIR does that with traits, or C++ traits, that is. We can do that with Rust traits, but in Pliron, Rust traits are nothing but interfaces. And there's a very neat little macro for implementing all that. So you can simply go ahead and say, look, derive this interface, which is terminator interface for this operation. The moment you do that, this is now an interface that we should be expecting from this this operation. So, and the way you create an operation, etc., is pretty straightforward. I've already got this up on the repo, so I'm not going to get into that. I think we discussed this a bit in the last stream, so I won't spend too much time. It's pretty straightforward. You don't have to worry too much. So those are the two things. You declare that this is a Pliron operation, and you let the op know that you'll be implementing all these interfaces. So for those interfaces, some of them are built in. That means they're available via the Pliron implementation itself. So you can go to built-in and you can see there's a bunch of interfaces that you can pick and choose from depending on your requirement. Or you'll have to go ahead and add one if that's not there. For example, there's a trait here that says, is this operation a unary operation or not? Right? Does this operation perform unary arithmetic? If so, that's great. Is it on integers? Then it should have already implemented the unary arithmetic op interface or trait. Straightforward stuff. All right. And if you jump into that, you'll be able to see that what do we need for a unary arithmetic op? You'll need that the operands are the same, the result type is the same, and you probably only get one result, right? So you want to go ahead and codify, or rather represent these constraints in code. And the way to do that, Trust is really good at this part. I would, in many ways, compare this with what is called type state programming. So you're effectively encoding the state of the state of various objects into a type in Rust. And then you're saying, okay, let me enforce this either at compile time or runtime, depending on what you want to do. All right. So that's something that you will see in this implementation as well. So the moment you do those two things, which is the operation, you mark your op with this macro, and you also annotate the interfaces that you wanted to implement, you're done. And that's exactly what I've captured here as well, just as an example. So if you take CLIF return, this return op is marked with this macro, and then I also want to derive this. This is just an example interface that you can see. The only thing that these interfaces must provide is a verify method, so that we are able to verify the implementation, right? We're not just doing XML programming over here, and we can actually, verify what do we mean by this op should implement this interface, that contract. How can it be upheld is through this. The other thing is you don't have to do it only here. You can also annotate the op interface implementation to an actual implementation for the op itself. That's just details, but that's what it is. Then, as I mentioned, the next thing is the op itself is verified. So whenever we call the verify method on the op, which is because we've already gone ahead and declared this macro. This macro is actually going to expand and provide, an implementation of this. The important thing that you see here is it'll provide a verify interfaces method. It's not going to do much. It's just going to call the verify method for each interface. That's about it. And obviously, those verify methods are something that you need access to. We'll get all that. All right. And then the way this verify interfaces gets called is through this trait that is implemented. It actually verifies everything, all right, before you go ahead and work it out. So this is how you implement at least a basic idea of implementing uh, a dialect in Pliron. In my case, I'm taking an existing IR and basically converting that into the Pliron version of it, which in this case is Pliron-CLIF. So the other things that you should be aware of are basically, for example, I'm doing this stuff here, right? I'm actually printing out whatever I've managed to convert. So this is the print. This is the print. And in order to actually do that, I need to implement the printable trait and the parsable trait for each op. Usually there's a very simple way to do this. Again, there's not a proc macro, but a simple canonical syntax that is a macro rules macro is available. This will effectively implement these two for if you just use this macro. But sometimes, this may not be what you want. And I've seen that happen. You may want to implement it yourself. And then there's also this implement verify, which is because you have to implement the verify method, which is this. You can do a default implementation. For return op, there's not much. So that's why we're doing this. I can show that to you with the return op itself. So you'll see that here. We have an implementation of impl verify success for this. But you won't see for return op, you won't see this canonical syntax. The reason for that is because there's another way to do the same printing as well. There's a format op, which does provide you the printability part stuff. So you don't need to do that by hand. There was something going wrong when I was using the macro. So the author mentioned you could simply go ahead and use this. I'm going to be replacing that macro, most of them, what that macro does with this procedural macro. So good. So yeah, that's that. And then the only other piece that you need to keep in mind is when you're actually implementing stuff, uh, this is not too relevant. All you need to know is those pieces. If you know that, you can go ahead and implement it you can go ahead and implement a dialect in Pliron, the basic stuff. You annotate a unit struct with the macro def op, and you derive pretty much all the interfaces that you want for it. And you can also format it and print it. And you need the verify. But if you just have these pieces, then you can go ahead and add an op in your dialect. It could be a translation from some other IR, or it could be your own custom IR that you're building out. It doesn't really matter. This one is basically talking about the nitty-gritty details. So just to sort of help you, the way you actually, the verify method is usually as this type signature. The verify method for every interface usually has this type signature. That's kind of what we want to store around. So we want to store that around so that we can, pull out the right verify method when we are doing the verification for all the interfaces that our op implements. That's what all the stuff is what you need for. Okay. Yeah. So that's pretty much what I wanted to show you. That's the op interfaces and the ops. Where have I actually implemented it? So if you go into this module from CLIF IR, you'll see that the entire implementation actually exists here. So you can go line by line. We have a convert type, which converts a Cranelift type to a Pliron type, operands, Cranelift operands to Pliron operands. And then we also have every instruction that I find in the Cranelift IR will be converted to the Pliron IR. This is where most of the work gets done. And then we've got blockwise. So you want to convert a Cranelift basic block to a Pliron basic block. This is how you do it. And then you convert the entire function itself, right? So all of that stuff is over here. So you can look at it rather than me talk about each piece. Just the basic outline. It's well documented, so should be pretty clear. All we do is, if you see this, so what we do over here is, let me just go here. So you can look at the unit tests that we've written. We parse the Cranelift IR because there's a nice parser already available. We don't have to do the parsing and stuff. And then you pull out for each function, you create your Pliron context and your conversion context. And then you start calling convert function, which will do the rest. Then the whole conversion process kicks through. We will be converting. A couple of things that I want to keep in mind is when we have converted, when we find the first instruction or the first basic block, once we've converted them, we actually want to store the fact that we've converted them somewhere so that we don't end up redoing that conversion. If we do that, we'll end up with, basically unlinked entities and stuff. So that's stupid. So you need a cache, and that's kind of why we will have what is called a conversion context, which is here. So you can have a hash map of the instructions, which is the Cranelift instructions to the Pliron instructions or the operations, and basic blocks, Cranelift basic blocks to Pliron basic blocks. At least these two, we need a cache of this so that we can go ahead and retrieve it once the first conversion is done. And yeah, then there's some things about RPO, etc. If you're already in the compile engineering space, this should be pretty simple. But since I'm not, I had to actually learn this stuff. It's very interesting. Yeah, so this was the typical implementation, at least for Pliron. Once we have a significant number of opcodes converted, we should be able to write a full-fledged program and then do the full conversion. Right now, we're doing opcode level conversions for unit tests. If you see them, you'll be able to see the control flows. You'll be able to see the branches. All of that stuff is already done. Once that's done, we just need to get to the part where we do a full-blown program is converted. Then I think it's good enough for the first commit, I guess. All right. So yeah, this one I wanted it to be quick because been away for a while, and we had to gather my thoughts and put everything together. So I hope this is useful because I'm pretty much going to be relying on this as I keep jumping between different projects. But if anyone finds this useful, please feel free to drop, a comment or any questions so that we can all, learn off of each other. Right. So yeah, I guess that's about it for this one. And I think I'm actually happy because I've stuck to my, time. All right. Thank you.